Other funny ones I'll keep to myself. So ask your TF. So if we want to actually insert S. Adams into this list, and the location at which we want to insert him is initially null, and null is suggested by all of these slash marks, that's just a null pointer, well, we have to go ahead and call mallocate and create a new struct, and inside of that is going to be apparently a string like S.Adams and then a new line character. But what does this thing probably represent? To the right of S. Adams in this data structure is another slash and another square. What does that represent, perhaps? Yeah, so it represents null. It represents a pointer. So in fact, these aren't strings per se. Each of these rectangles that represents a person, S. Adams, J. Adams, and so forth, is apparently instead a struct, inside of which is a string, just like we saw previously. Inside of a student is an ID and a name and a house, the last two of which are strings. Here, apparently, one of these structures, let's just generically call it a node, N-O-D-E. So this might just be a string as part of the struct, and then this other thing is just a pointer. And as we typically draw pointers as squares, that's probably 4 bytes or 32 bits. And it's null because there's no one else in this data structure after S. Adams. But apparently W. Floyd and J. Adams share the same birth date of the month. And so we have to start chaining those two guys together in order to put them at the same location. Now this too is not ideal. Right? This does avoid what problem? This is better than this design. Why? What problem do we avoid completely? Or theoretically? What's that? Linear time. So it actually, not quite. So we'll come back to that. But what was the biggest deal breaker with this thing besides collisions? It's limited, right? It's finite space. We had 26 buckets in this case, which means if we try to insert the 27th person, my God, we have to jump through this hoop of reallocating more memory, copying everything over. And again, this is typically not an ideal solution. So this approach, called separate chaining, definitely solves that problem. And I say theoretically because you could still run out of memory in total in your computer. So you might not be able to allocate more of these structures here. But that's only if you're talking like 2 gigabytes or something crazy inside of the program. So this, at least, is completely dynamic. But technically, the running time now of finding someone in this data structure, in this ideal case, it's still constant time. In the ideal case, it's just S. Adams. He's the only guy there. We jump right to that spot, and bam, we found S. Adams. But if you kind of do this over time, in the worst case, what's your data structure going to look like? If this is my array of pointers, and I'm chaining off of this all of the actual people, what's a worst case scenario in a class of students when we're trying to insert them into this array? Yeah, they all have the same birth date of the month, or in our previous example, their names all, oddly enough, start with the letter A or some specific letter. So even though we might have a really smart design, it's possible that just by bad luck, these things could be ending up here, here, and so forth. So what's this devolving into, despite the vertical aspect of this picture? It's just a linked list, right? So the running time potentially of a hash table even, and this again is called a hash table. This is just a different version of it that's using separate chaining. Well, even in this case, it could devolve back into linear time. But if we do this intelligently and we actually use, let's call it a hash function, that's more intelligent than just saying use the first letter of their name or use their birth date, the day of the month on which they were born. Because these clearly lend themselves to perhaps disproportionate collisions. You know what we could do? In the best case, none of these chains, so to speak, is going to be that long. This one might be too long. This one might have 2 nodes. This one might have 2 nodes. Ideally, if we have a whole bunch of pointers vertically, and we create these chains laterally, ideally, we're going to have these chains being of roughly equal length. So ideally, what we have is a running time of big O of n, where n is the total number of elements inside of this structure. And let's call it arbitrarily k, where k might refer to what here? Why do I divide by k? The goal is to answer the question, what's the running time of search ideally here? The size of the array, the size of the hash table, the height of the hash table. So if this is height k, so this is either 26 in one example or 31 in another, that's what we mean by k. So this is better, right? Big O of n over k is better than big O of n, but only in the real world, right? If k is a fixed number like 26 or 31, what have we been doing for the past few weeks? we always kind of cross that out. So here's where theory and practice kind of start to clash with one another. In the real world, n over k is absolutely better than n. Just arithmetically, you divide some number by a positive number, and you're going to get a smaller number than the original number, right? That just works out that way. So in the real world, you're going to spend less time or use less memory if you're dividing by that factor. But asymptotically, sort of pre-quiz zero, in pre-quiz zero terms, we always said that this is still big O of n. So here's what's kind of neat, and also what's neat in particular about problem set 6, which is this speed-oriented spell checking challenge. Well, yes, it's still big O of n, this notion of a hash table, whether we implement it like this, which has a couple problems, this, which is better, but still has some problems. In the real world, doing something in, say, 100 seconds is absolutely going to be slower than doing something in 10 seconds if k is 10. Right? So any kind of real world improvement we can make actually benefits real people, even if the mathematicians and theorists might say, asymptotically or with big enough numbers, this is really quite irrelevant. But it's not irrelevant in the real world. So this promised land of having a constant time lookup is really only in an ideal world. You can construct, in fact, what are called ideal hash functions, which indeed take some data structure like this, or even one like this, and if you're smart enough and put enough time into the process of writing the hash function, the thing that determines where an input goes, well, you can actually come up with an ideal hash function, which will literally put everyone at a specific place without any collisions. But it requires a lot of work. And so invariably, every semester we have folks, particularly the hacker types, that try to implement for pset 6 an ideal hash function, and then they read the fine print, where you're not allowed to do that in advance, because you have to know something about the data in advance to actually construct that. So instead, you have to come up with better hash functions. A hash function that we've been using right now has actually been simple. You hand me a person. I look at, I being a hash function in this story, I look at the first letter of their name, and I return a number between 0 and 25. So some letter of the alphabet. Or you hand me one of these apparently famous people, and I hand you back a number, which is the date of their birthday. And then you use that to index into an array. So a hash function generally takes as input some structure or some string or some number, and then returns a number within a specific range. What's that range? Well, in this case, it's 26. In this case, it's 31. It's within some specific bound. So if you think back to your C operators, the modulo operator is actually quite common in this context, when you want to compute something and then return a relatively smaller number. So let's do better. When I hand you the name of a person, if it's apparently not quite ideal to just look at their first letter, the first letter of their name, what could you do that's a little better? That's still predictable, that you can repeat this process, but it's not as naive as just looking at the first letter. What might you do instead? Right? All you're given is a string, and you have to somehow give me a number between, let's say, 0 and 26, 0 and 25. But again, this is arbitrary as well. What could you do? Besides looking at just the first letter, what else could you do? Right? I mean, that's actually pretty reasonable. You could look at the second letter. And what could you do? Well, remember that in C and in programming in general, a string is just a bunch of characters. A character is just a number. So you can already think back to pset 2 with Caesar and Vigenère. You can already kind of treat strings as numbers. So maybe we could do something arbitrary, but perhaps predictable, like take the ASCII value of the first letter, add it to the ASCII value of the second letter, and that gives me a sum. And that sum might be a little too big. It might be 100 plus or something. But that's OK. I can just use the mod operator, the percent operator in C, and give me a number between 0 and 25. Now, whether or not that works is kind of unclear, right? There's still some dependencies in the real world between first letters and last letters. Like, you don't generally see a name that's like ZK. You might see ZO or ZI, but that's going to be more common. So that might not be quite enough. So what can you do if the first two letters might not really be sort of independent or random enough? We'll do the first three or the first four. And in fact, a common hash function is, given a string, is to actually add up the ASCII values of all the numbers and then take some modulo operator of it to get back a smaller number. Or you can do even much fancier things, especially if you know in advance what the data is going to look like, whether it's human names or the like. So how can we represent, say, let me say something like this? So we can do a little better than this, in fact. If we introduce the notion of a tree, we can actually, and let me tease you with a crazy looking picture, we can actually implement a little something that looks like this. And even though I just said that with a hash table, we can only get to, say, linear time or linear divided by k, where k is some constant, I actually can retract that a bit. If you're willing to spend a lot more RAM, a lot more memory, and have a lot of arrays inside of your program, we can actually boil down the problem of looking up strings or doing dictionary lookups in literally constant time. But let's pause for a couple minutes for a musical interlude by our own Ansel Duff again, and then we'll return in 5 minutes and answer how this can be achieved. OK, we're back. So before we get to this amazing new data structure that's going to solve all of our problems, let's just paint a quick picture here of this, just to make clear how we could even go about implementing this so that it's not completely in verbal pseudocode here. So here was, so far, our best implementation, best only in as much as it is dynamic and can grow to fit as many things as we actually have, even though we might still get some long chains. And in the very worst case, we might get a lot of Alice names, A names, A names, A names. So it could devolve into just a linked list, but hopefully that's not actually the case. Well, how do we implement each of these things I called a node before? Well, again, we just need a way of expressing that picture. So here's a struct called node. And inside of the curly braces, I have just two fields. One of those fields is going to be a string, so to speak. So it's an array of characters. And it's an array of characters, each of which is of length plus 1. And because it's written in caps, I can infer that's some constant defined somewhere. And it's, I don't know, maybe it's 16, maybe it's 128. It's some relatively reasonable, if large, constant that I'm assuming all of my words are shorter than. And the plus 1 is always for the \0 for the null terminating character. So this thing, though, is that 4-byte pointer that allows me to chain S atoms to someone else, to someone else, to someone else. And the reason that there's this apparent redundancy between the word node here and node here is, again, the rule of thumb is if you're creating a data structure inside of which you want to have a pointer to another one of yourself, a struct of the same type, you need to be able to express that with some word. So if you say struct node or struct foo or whatever you want to call it, but for consistency I'd use the same, we can now, because we've declared this here, refer to it inside of the structure. But henceforth, thanks to the type def, we can just call this thing a node. So that's how we might actually implement that in code. But let's actually now use this same idea, these pointers and these linked lists, so to speak, and those concepts from Monday to start making more interesting structures. So this is what in computer science is generally known as